Hi there, and welcome back to the channel. Throughout this series of videos, you will be introduced to topics in optimal control and estimation in a way that you can draw almost complete idea about optimal control and optimal observers. Most of the introduced materials during this journey is borrowed from the book, Applied Optimal Control, Optimization, Estimation, and Control, which is written by Arthur Bryson. This is the 7th part of the series. In the previous part, I have covered the conditions for obtaining optimal control actions for single-stage dynamic systems. I highly recommend watching part 6 before this part, as similar techniques are applied but in much simpler way. In this video, I am going to extend the concepts of solving optimum control problem for single-stage systems and deal with systems that have multistage dynamics and index of performance. Multistage systems are also parameter optimization problems. Simply consider x of 0 to be the given current state of the system. Also, suppose that we have a control action vector u of 0 along with a pre-specified dynamic of the system at time 0, f of 0. All of these three elements can predict the future state of the process given as x of 1. Once again, suppose that we have a control action at time t equal to 1, given as u of 1, as well as we know the dynamic of the process at time equal 1, given as f of 1. Similarly, these new set can produce a future state of the system known as x of 2. Following this mathematical process, we can predict the state of the process at any given time. Please keep in mind that in order to predict the future state of the process, we need three information, which are the previous state of the process, the applied control action, and, of course, the dynamic of the process at the given time. This mechanism can be mathematically simulated through the following relation, where it is assumed that the current state of the process is given as x of 0 and I is changing from 0 to n, where n is known as the prediction horizon. Of course, x of I is a sequence of n-dimension vector, while u of I is also a sequence of vectors but with m dimension. The real question here is how to choose the values of the control action vectors u of 0, u of 1, all the way to u of n-1. As we are dealing with optimal problems, we can say that we need to choose those control vectors u of I that minimizes some index of performance given as the j function. Let us burn some seconds to observe the terms of the j function here. There are two terms. The first term, phi of x of n, is known as the terminal term where, as can be seen, it is defined at the end or terminal given as the quantity n of the optimization problem. As I stated earlier, n is known as the prediction horizon. The second term is a summation function. This term accumulates the performance of the system according to some index, here known as L of I, from the very first time of simulation, namely at time 0 all the way to the time n-1, which is right before the terminal time at n. Usually both functions phi and L have same structure, and the well-known structure is the quadratic function. As we dive deeper in the optimal control, we will face different shape and structure of this function, so be patient. One last point to be stated before processing with our subject is that, for now, the dynamic of the process is assumed to be time-variant dynamic, which means that at each given time index I, the dynamic of the process changes. And this is realized with the function f of I. Okay, let us continue with our main subject. As we did with single-stage systems, the given control problem can be easily converted into a control optimization problem by simply adjoining the constraint, which is the process dynamic, to the index of performance given by the j function to produce the function j bar. Here, lambda of I is a multiplier sequence. Let us focus on this relation deeper. For convenience, let us define a scalar sequence hi as shown, in which I is taking values from 0 to the end of the horizon n. And if we change the indices of summation on the last term, we will end up with following expression for the function j bar. Please pause the video and spend few seconds here to observe what just happened. It is quite simple to follow. Okay. Now, we are ready to drive conditions on computing optimal values for the control sequence vector u of I. The first step would be considering differential changes in the function j bar due to differential changes in the process states, as well as the applied control actions. This differential change can be formulated as shown. Please watch the first few minutes in part 5 of the series to understand what differential changes mean in a function. If we look closer, we may come up with an expedition of lambda of I from this expression. But, to avoid the tedious procedure of determining the differential changes delta x of I that is produced by a given delta u of I, we could, however, choose lambda of I to be as shown. This assumed form for lambda of I can be further simplified utilizing the defined formula for hi as shown. Of course, this new relation is defined all over the horizon from I0 to n. To deal with lambda at the terminal, namely lambda of n, we can add a terminal boundary condition as shown. With these two new expressions, along with the initial given state of the process, which makes the delta x of 0 to be 0, we can further simplify the delta j bar to be as shown. In this new relation for delta j bar, please keep in mind that the partial derivative of hi with respect to u of I is the gradient of the function j or j bar with respect to u of I while holding x of 0 constant, and at same time satisfying the process dynamic along the horizon. Also, at this point, it is clear that a stationary value of j bar, and hence our original cost j, for a given process state x of 0, will be obtained if the partial derivative of hi with respect to u of I along the horizon is equal to 0. To sum up what we have covered so far, we can say the following. In order to find a control vector sequence u of I that produces a stationary value of the performance index j, we need to solve the following difference equations. 1. The dynamic of the process. And 2. Lambda of I from the shown condition. The control vector is computed by seeking a stationary point of the hi function. This requires that we have the following relation to be true along the horizon n. Please keep in mind that the boundary conditions for the first two difference equations are split, which means that some are given for I equal to 0, which is the initial state of the process, while others are given at the end of the horizon n, such as lambda of n. Based on what have been stated here, we can categorize our control problem into a set of difference equations as shown and a set of boundary conditions as shown. This kind of problems are known as two-point boundary value problems, and they are sometimes rather difficult to solve, even with a high-speed computer. From this problem, one can observe that the first two difference equations are coupled as u of I depends on lambda of I through the last difference equation. At same time, the coefficients of the second difference relation depend on both x of I and u of I. One last point that needs to be mentioned here is that in order for the function j to have a local minimum, not only the condition of the partial derivative of hi with respect to u of I has to be 0, but also the second order of derivative of the function j has to be greater than or equal to 0. Before proceeding to an example, let me show the big picture of the problem we are dealing with in this video. In the two-point boundary value problem, we have an initial value for the undertaken process known as x of 0. This initial state vector along with a control vector, u of 0, and through the dynamic of the process, f of 0, all determine a future state of the process x of 1. By its turn, x of 1, and with the help of the u of 1 along with the process dynamic f of 1, the state of the process at time I equal to 2 can be computed. Following this procedure, any future state of the process can be predicted. I hope at this stage you have realized that we are dealing with a process dynamic that is time variant. As we went through the procedure of predicting a future state of the process, we were assuming different values of the process dynamic at each time index of I. And, of course, we do not forget that the control sequences u of 0 to u of n are computed by minimizing the performance index function j. This function of performance, in general, has two terms that are defined at two periods of time. We have phi of x of n, which represents a cost of the system state at the end of the horizon. The second term, on the other hand, is the summation or accumulation of some combination of the process states and the corresponding applied control actions that are time-indexed from the initial time to one time before the end of the horizon. This problem can be complicated even more by, for instance, adding some constraints of the states or control actions all over the horizon or at the terminal only. As we have passed over the introduction of the optimization control problem for this video and the derivation of the conditions for solving for optimal control actions, we are ready to apply these concepts on a simple control problem. The example we are dealing with has a quadratic performance of index along with linear system dynamics. So, it is required to find an expression for optimal control sequence along some horizon n which minimizes the shown quadratic performance of index or cost function. In this function, the quantities a of I and b of I are pre-defined positive definite matrices. The linear dynamic of the process is given by the following state space realization where the initial state of the process is known in advance. Before continue with the solution, let me state the problem as following. First, we have the following cost function or performance of index. This function has to be solved such that the dynamic of the process is satisfied starting from the given initial state. We can compare this problem with our previous problem as shown, where simply phi of x along with Li of x and u of I are given as shown. Now let us starting to find an expression for the optimal control sequences u of I. As a first step, we can define the function hi as shown, where the first term is simply the expression that is found under the summation portion of the j function, whereas the second term is the process dynamic. Do not forget that we are combining these two terms via the multiplier lambda, which is defined at one time ahead. At this point, we can treat this problem as a two-point boundary value problem. First, we have boundary conditions in which the first boundary condition is the initial state of the process x of 0, which is given by the original problem. For the second boundary condition, we can apply its condition on the phi equation, which gives the shown lambda of n condition as well. The second step would be driving the difference equations that we need to solve for. The first equation is the process dynamic that has to be satisfied at each time index. The second equation comes from applying the relation of the lambda of I on both the process state as well as the function Li. This adds the following relation to our set of difference equations. The last equation comes from the relation of partial derivative of hi with respect to u of I. As with the condition of lambda of I, this requires using both process dynamic and the function of Li. This step adds an explicit expression for the control action u of I. If you watch closely, this expression is in term of lambda of I plus 1. Now, if we take this expression and substitute it into the process dynamic x of I plus 1 and at same time considering the expression of the lambda of I plus 1, we will end up with a set of two difference equations that need to be solved simultaneously. Of course, we need to satisfy the boundary conditions as well. These two relations are coupled set of linear difference equations with two-point boundary values that produce a sequence of control actions u of I that minimize the given performance of index. Please keep in mind that when we say minimize, we need to check the second derivative of the cost function with respect to the control sequence and test the definite of the resulted matrix. This step is ignored here because, as we will see later, for quadratic cost functions, the positive definite of the predefined matrix A of I in the cost function is essential for having a minimum optimization problem. The problem covered throughout this video was in the discrete form. However, in the next part of the series, we will extend the concept presented here to continuous systems with no terminal constraints and fixed terminal time. I truly hope that this part was helpful. Thank you for watching this video. And please consider subscribing to the channel and giving a thumbs up to the video. See you soon. Hopefully.